In this video, we'll discuss the addition rule. The first thing we're going to talk about is called mutually exclusive events. Two events A and B are mutually exclusive. If when A occurs, B cannot occur. So if A occurs, then B cannot occur. It means that they're mutually exclusive. Or another way we look at it through these things called Venn diagrams. A Venn diagram represents events as circles, and then the entire rectangle around here, the box around this, is going to be the sample space. So all the events occurring are inside the sample space. Here you have two events, event A and event B. And what this is saying that if A occurs, then B cannot occur. So also if B occurs, then A cannot occur. So for instance, the probability of being left-handed or right-handed. Well, if you're left-handed and you define yourself as left-handed, then you can't be right-handed. So those are mutually exclusive events. The probability of smoking or not smoking, or being a non-smoker. If you smoke, then you can't be a non-smoker, mutually exclusive. On the other hand, if two events can occur at the same time, such as the probability that it rains tomorrow and you get your hair cut, well, those events are what we call not mutually exclusive. They're more independent. Independent means that if one event happens, the other one won't affect the other. So it can happen, but it won't affect the other. And the way we graph that in a Venn diagram is we have event A here and event B here. And there's an overlap now. So when two events are independent, they get this overlap or this jointed area right here. And we call this a joint. And this right here, we're going to notate these. This can be written as what we call A union B. A union, and this is the symbol for union. A union B means, or the word union means the word or. This means A or B. This is what we call the intersection. And it's written as A and B. And so the intersection, the word for that is and. And it means that they can happen at the same time. So when we talk about mutually exclusive versus not being mutually exclusive means that if event A happens, event B cannot happen. That's different from independence. Independence means that if event A occurs, it has no effect on event B occurring, which means they can happen at the same time, which gives you this joint. And it just so happens that this joint right here is going to be the independent section of whatever occurred between A and B. And now, so from all of that, we're going to get what's called the addition rule. And the addition rule says if two events A and B are not disjoint, which means they're jointed. So let's draw a Venn for this real quick. We know a jointed Venn looks like this. You have event A occurring here and event B occurring here. Neither jointed events because they have a intersection, A and B occurring. But if two events A and B are not disjoint, the probability of both events occurring can be found by the addition rule. And the addition rule starts off as A union B. Remember, union means or. So this says A or B. Well, the probability of A or B is equal to the probability that A occurs. So here's the probability of A plus the probability that B occurs. Here's the probability of B minus the probability of A and B. And A and B is this part right here sitting on the inside of the joint. Well, why are we subtracting off A and B? Let's go through that again and notice what happens. When we do this, the probability of A is sitting here, right? It's all of this area right here. Then we're going to add the probability of B, which is all of this area right here. What did you notice there? Well, notice that there's an overlap taking place between A and B. If you counted that overlap, how many times? Twice. So what do we have to do to fix that? We subtract it off once. This gives us what is known as the addition rule. And it's just adding the events and it's subtracting off the intersection because you've added it twice. And there's a nice property that follows from this if the two events are mutually exclusive. What does mutually exclusive mean again? Mutually exclusive means that if event A occurs, then B cannot occur. Or if we draw the Venn for that, here's event A, and here's event B. Again, there is no overlap. So this time when you write this out, the probability of A occurring is here. The probability of B occurring is here. Since they don't overlap, we don't have to subtract anything off, and we get this right here. So let's use an example to illustrate this thing. So there's a card selected from a standard deck of 52 playing cards. Find the following probabilities. If you don't know what a standard deck of 52 playing cards are, in a standard deck there are 4 suits of cards, each having 13 cards, ranging from 2 through 10 numbered cards, and then Jack, Queen, King, and Ace. There are 2 black suits, which are the clubs, that look something like this, and the spades, which something like this. So clubs and spades are the 2 black suits. And then there's 2 red suits, which are the hearts and the diamonds. And so there's these 4 suits of, remember, 2 through 10, Jack, King, Queen, Ace. That's 13 cards times 4 is equal to 52. Jack, Queen, King, Ace are considered to be what we call face cards. And every suit has these 13 cards in it. So in the standard deck, here's what you have. And we're going to use these to answer these probability questions. So when you answer these questions, here's how it works. The probability of the card is a 4 or an ace. So you have 2 events occurring. The card can be a 4 or it can be an ace. So the question you need to ask yourself, first off, is this a jointed or disjoint event? And here's how you answer that. Are there any cards in the deck that can be a 4 and an ace at the same time? Well, are there any 4 and aces at the same time? No. And we can write it out like this then. The probability of the card is a 4. Probability of being a 4. Or, that's the union, an ace. Well, what is the problem? How many 4s are in the deck? Well, there's 1 4 in every suit. So you have 4 suits. That's 4. Out of how many total cards? 52. And because these events are disjoint, meaning you can't be a 4 and an ace at the same time, or there are no 4 and ace at the same time in the deck, you can add their probabilities. So 4 out of 52 plus. And an ace, how many aces are in the deck? Well, there's also 4 of those in each, there's 1 in each suit. 4 out of 52, that's equal to 8 out of 52. And you may reduce that if you want to, but we're going to leave it like it is. Let's look at the next one. The probability that the card is a face card or a heart. So the probability of being a face card, and again, the word or means union, a heart. Well, how many face cards are in the, so the question again, is this a jointed or a disjoint event? And really what you're asking yourself is, are there any face cards that are also hearts? And yes, there are. So this is a jointed event. So when we calculate, we're going to calculate the joint part. So here's how we do it. We do probability of the probability that a card is a face card. Well, how many face cards are there? There's 4 hearts, there's 4 diamonds, there's 4 hearts, 4 diamonds, 4 clubs, and 4 spades. And there's Jack, Queen, King, Ace in every suit. That's a total of 16 face cards that are hearts. Plus, how many of these cards are hearts? So out of the 52 cards, how many are hearts? Well, there's a suit of hearts, which is 13. So that's 13 out of 52. Now, the problem with this, though, is that we've done what? In this 16 out of 52 and this 13 out of 52, we counted what twice? We counted the face cards that are actually hearts. Well, how many face cards are actually hearts? There are 4 face cards that are actually hearts out of the 52. So we have to go back and subtract those out because we've counted them here in this suit Jack, Queen, King, Ace of Hearts. And we've counted this suit, which are Jack, Queen, King, Ace of Hearts. We've counted it twice. We only need it once, so we'll subtract it off. And when we do that, we get that this is equal to 16 plus 13 is 29, minus 4 is 25. So that's 25 out of 52. The last one says the probability that the card is black or an ace. So the probability of being a black card, and again, or an ace. So question is, are these jointed or disjointed events? Are there any black cards that are aces? And the answer is yes. There's the ace of spade and the ace of diamond, which are both black cards and they're both aces. So we set it up like this. How many black cards are in the deck? Well, half the suit is black, so that's 26 out of 52. And again, we have this word or, so that means to add, plus. How many of them are aces? 4 out of 52. But what did we do in that process? We've counted the black aces twice. So we need to subtract out how many black aces are there? Ace of spade, ace of club. So that'll be 2 out of 52. And that's equal to, well, 24 plus 4 is 30, minus 2 is 28, 28 out of 52. So when you do problems that involve the word or, where they're checking for joints or disjointed events, if the events are jointed, you have to go back and subtract something off. If they are disjointed, you could just add the events like they are. So let's do an example where we actually use a Venn diagram to calculate this. And this example says we have randomly selected 100 students enrolled at Star College. 55 of these students will enroll in the math course, 35 will enroll in an English course, and 10 will enroll in both. They want us to find the following probabilities. So to set up a Venn, you always start with the jointed part of the Venn. So you're going to start here. You're going to try to fill out this part first and then work your way out. And our two events are, let's take an event. We have the event that a person is in math, which we'll call M. Or we have an event that a person enrolls in English, which we'll call E. So we have M, event M, and event E. And here we know that out of 100 students, 10 will enroll in both. So that will sit here. This right here is the probability, or this right here is M intersect E, math and English. And we have 10 people sitting here. So we've taken care of this part. The next part says 35 will enroll in English. So let's work our way out. Well, we already have 10 enrolled in English. So how many is that going to leave us left to be in just English alone? Well, 35 minus 10 is 25. And if you add these two up, 10 plus 25 is the 35 people that are in English. But 25 of them totally take English. The next part, 55 will enroll in math. Well, again, work your way out. You already have 10 enrolled in math, so how many is that going to leave in solely math? 45, because 45 plus 55 is, 45 plus 10 is 55. Now, we have a total of 100 students, right? So these numbers should add up to 100 if we did this correctly. Well, you get 45 plus 10 is 55, plus 25 is 80. So we're missing 20 people. Well, why are we missing 20 people? That's because not everybody's going to enroll in math and English. And we just said it's 20 people that don't enroll in math and English. Where do those 20 people sit at? Well, they're still part of the sample space. They just sit out here. So this is how you construct a Venn. You always start from the inside and work your way out. And the first question says, what is the probability that a randomly selected student enrolls in both math and English? So the key word here is and we're looking for the probability of A and B. Well, we can see that how many people enroll in both math and English? 10. So it's just 10 out of how many total people in our sample? 100. That's just 10%. What is the probability that the student only enrolls in English? So only English is sitting out here because these people are math and English and these people are just math and these people don't even take the course. So we're going to do the probability of only English. We write English and math, C. What does that math C mean? Well, C means not, complement. So English and not math, what you're looking at here. And that's equal to 25 over 100 or 0.25 or 25%. The last question says, what is the probability that a random selected student does not enroll in math or English? So the probability of math complement, not math, enroll in math or, so union, E complement, math or not English. Well, that's who's not enrolled in math or English? These 20 people out here. Says 20 out of 100 are 0.20, which is 20%. The last example is going to look at what we call a two-way table. In a two-way table, you have values that sit either inside of the cells, like here inside of the cells, or values that sit outside of the cells. The values that sit on the outside of the cells, here and here, form the totals. These are called marginal probabilities. Why are they called marginals? Well, where do they sit at? They sit in the margins. The values on the inside that sit inside of here are called your joint probabilities. Why are they joint probabilities? Well, notice this. If it's a joint probability, it means they can occur at the same time. So if you're talking about, in this particular case, RH factor being positive or negative, and blood type being OAB or AB, you can have positive RH and have O blood. What you also need to notice is that when I look at this, I can see that on the outsides, though, can I be positive and negative at the same time? No. Can I have O blood, A blood, B blood, and AB at the same time? No. The events on the outside are always going to be disjoint. So the marginal events will always be disjointed events. And so we can read this table like this now. If you notice, if you go down a row, right here, for instance, coming down this row, it adds up to all the people who have O blood. Coming down this row adds up to all the people who have A blood. Coming down this row adds up to all the people who have B blood. And coming down this row adds up to all the people who have AB blood. Going across, if you go across here, you can add up to all the people who have positive blood. If you go across one more time, sorry, I'm trying to switch my colors on the fly. This adds up to all the people who have negative blood. So when I look at this table, it's giving me all of this information here. All right. And what I want to know is I want to find the probability that the donor has type O or type A blood. So let's get rid of all of this stuff so it doesn't distract while we do this. So now when we look at this, if I want to find the probability that a donor has type O or type A blood, I'm going to look at, first off, can you have O and A blood at the same time? No. What does that mean about these two events then? If the one occurs, the other cannot occur, what does that tell me? That these events are disjoint. And if they're disjoint, I should be able to add their probabilities. Well, what's the probability a person has type O blood? That's it here. So the probability of O or A is equal to the probability of O plus the probability of A. And notice I don't need the minus probability of A and B because there is no A and B. You're either O or you're A. So that'll be 184 out of the total, which is 409, plus 164 out of the total, which is 409. And that's equal to 184 plus 164, 348 out of 409. or the decimal is about 85%. So that tells me that the majority of people in this sample have type O or type A blood. The next question says, find the probability the donor has type B blood. R is Rh negative. So the probability of having type B blood, R, an Rh factor that is negative. And so that's equal to, we look across this time, well, who has type B blood? The probability of type B blood is 45 out of 409. Plus, the probability you have Rh neg well, Rh negative blood is 65 out of 409. But the problem with that is that what have we done? Well, going down these rows again, you notice you have type B right here, negative right here. What did you do? You've added the number, you added the 8 twice. Well, why did you do that? Because those are the people that have B blood and they have Rh negative blood. So what do we need to do to fix that? We subtract off the 8 people who have that type of blood. And we get 45 plus 65 minus 8 equals 102 out of 409 people, which the decimal for that is approximately 25% of the people have this.